Welcome everyone. We're carrying on with momentum, and today we're going to look at Newton and momentum. I can hear the groans because you're going, oh, Newton's laws. But it's okay. They're fun. We can do this. This is such a nice section. So, here we go. And I know we started with this question last time, but it's actually quite important because we've thought about why is it difficult to stop a rugby player when they're running? So now, last time we spoke about the fact that they'd have lots of momentum. But to stop someone, a rugby player, from moving, we need to apply a force to them, which means we need a net force, a resultant force on them that's going to change the way they're moving. So what does that mean for us? It means if we're going to change the rugby player's momentum, we need to apply a force to it. As soon as we start talking about applying forces, we're talking about Newton's laws, okay? And Newton's first law, second law, and third law play a role. They don't just disappear because I'm talking about momentum. They're all interconnected, okay? So, last time, definition, equation, and property. So today, we're going to look at Newton's laws. And what are our key words? Okay, I'm going to do this so it doesn't go away. Newton's first law. We're going to go through the statements of that. Newton's second law. We're also going to go through about that. And then, of course, we've got net force. Now, that's a term that you should really know. None of these three words and terms shouldn't be new to you, okay, because you've done them in previous studies, so they shouldn't be new. Let's look at Newton's laws. So, the ones we're specifically talking about is Newton's first law. And remember, Newton's first law, and I'm just going to write it as a sort of summary, is the one that says that an object will be at rest or constant velocity when the resultant force on it is 0. Now, that's not the statement you're going to put into a test or an exam. It's just reminding you. Okay, so remember, an object will continue moving or remain stationary at a constant velocity if it's moving at a constant velocity if there's no net forces acting on it. Okay, Newton's first law. Newton's second law is, we're going to change it a little bit. So we're going to look at it in terms of momentum, and this is going to be new. So you need to remember, when we did Newton's second law in previous studies, we went F net equals ma, okay? And you had a very long definition that said to you that when a net force acts on an object, the object will accelerate in the direction of the net force with an acceleration that is directly proportional to the net force and inversely proportional to the mass. So when we looked at this Newton's second law normally, it was all about the acceleration, and we recognized that if we increased the net force, we'd increase the acceleration. If we made the mass bigger, we would make the acceleration smaller. But it's got this whole term of acceleration in. And momentum has to do with velocity. So what we're going to do is go, how can I relate Newton's second law with this whole resultant force to what's happening with momentum? All right, so we're actually going to have to think back a little bit to what we know about the definition of acceleration. So as we're going through this, I want you to be thinking about what is the definition of acceleration? How do we know accelerations happened? and I'm deliberately only using the word acceleration. We don't use deceleration, okay? So here I'm not just talking about if an object gets faster, but remember objects can get slower. So it can decrease in velocity. All right, so have you ever thought about, probably not, but we're going to go with it, how Newton's first law applies to momentum? Now we've got to think about this and go, well, first of all, first law means there's no net force, okay? And I just want to check there we go. So when I look at this, I'm going P equals mv. We're going to keep that in our minds. So a body will remain, this is the official definition, will remain at rest, in its state of rest or motion at constant velocity, unless a non-zero force or net force acts on it. So if I look at momentum, that velocity is a constant velocity. So if an object has a constant momentum, its velocity isn't changing, which then means it will keep on at that momentum unless something changes it, unless a net force acts on it. So the two are related in the sense that we only look at constant velocity for the momentum for now. Absolutely, momentum can change, but then it's not Newton's first law anymore. Then we've got a net force acting on it. Then it's going to change. But when I look at this equation in its simplest form, with just the v there, it's constant velocity. Now, obviously, an object could be stationary. If an object's stationary, it has no momentum. And it will continue to have no momentum unless a force acts on it, unless there's a net force acting on it. Okay? So that's how the two go together, which I've just done. Okay, so in the next section, okay, so now we've looked at first law. First law isn't a lot in terms of momentum, okay? Second law gets a little hair-raising because, like I said, we had acceleration in it. So we're going to take a short break. When we come back, I'm going to show you, or we're going to talk about, how momentum gets related to Newton's second law. Okay? So we'll be back in a couple of minutes. Welcome back. So, last time we started looking at Newton's laws, okay, in the last part of the lesson, and we spoke about Newton's first law, but now we've got to say what happens when the velocity of an object changes. Now, this is a very open-ended question because am I asking you about force? Am I asking you about the effects of a force? Am I asking you about momentum? But of course, we're working on momentum. That's the theme of our lesson right now. So obviously, I'm asking in terms of momentum. Okay? I didn't ask how does the velocity change, because then that would be force. Only forces can change the velocity. So if the velocity of an object changes, that must result in the momentum changing. Okay? You're going to hear this lots. Why? Because momentum is mass times velocity. So if the velocity of an object changes, its momentum must change as well. Let's look at this. So, the issue is this. To change the velocity of an object, we must have a net force. We must, okay? Newton's first law says to us that it will actually stay at constant velocity if there's no net force. If I want the velocity to change, I need a net force. So I need an acceleration. And I'm not saying that means it's going to get faster or slower. It could be either. So we need an F net. Now we're going to develop something here, okay? F net, Newton's second law, is equal to mass times acceleration. Now, before the break, I asked you to keep in the back of your mind what the definition of acceleration is from equations of motion, which you did previously. So now we've got to think about it, and we go, well, acceleration is defined as the rate of change of velocity. So it's how quickly or how slowly velocity changes. It doesn't mean that it's going to get faster, and I'm making a big deal out of this because in everyday language, we use the word deceleration to mean slowing down, and that's fine in everyday language. But in science, we use the term negative acceleration if it's slowing down, because it's about direction. Because if it's slowing down, it means the force is moving against the motion, and that's usually given as a negative, okay? So, acceleration, rate of change of velocity. How do we put this as an equation? Well, acceleration is the rate of change. So it's the change in velocity. Remember, delta, the triangle, delta means change in, okay? So we would have also written it like that, where we have VF, final velocity, minus initial velocity. It's always final minus initial. Now we go, okay, so I know what acceleration is. Now we're going to do a little bit of a maths thing, okay? So I'm going to take this part of the equation, and I'm going to substitute it in there. So I'm going to take the A away, and this means my equation becomes this. Now we're starting to see something that looks a little familiar, because I've got a mass and I've got its velocity, and we know that momentum is mass times velocity. But that's a change in velocity. So actually, I can rewrite this equation again. Okay, so now I'm going to expand it. So instead of delta V, I'm going to put this. Okay, so keep with me. So F net is equal to m VF minus VI over delta t. All right, I hope you haven't lost any of you. I'm going to multiply the m in. Okay, so mVF, mVI. Oh, now I'm hoping some light bulbs are going off, because if we look at this, okay, let's use one. That's a momentum, and that's a momentum. But it's momentum at a specific point. That would be the final momentum, the momentum after the velocity's changed, and that would be an initial momentum. So actually, I could write this again as being F net equal final momentum minus initial momentum over delta t. So my net force would be equal to a change in momentum divided by time. That change in momentum comes about because the velocity changed. Why did the velocity change? Because we exerted a force on the object. So we had an equation that said mass times acceleration. Sometimes we don't know what the acceleration is. We only know how the velocity changed. So we can also say that F net is my change in momentum. We've taken an equation that you knew, and we've manipulated it to get something else that we can use in a different context. Okay, so yes, F net equals MA is useful, but sometimes this change in momentum is actually more useful. It depends on the information we're given. All right? So that gets us to a different statement of Newton's second law. I gave you that nice long one where the acceleration is in the direction of the net force, with the acceleration being directly proportional to the net force and inversely proportional to mass. Yes, long. Lots of words. If I write it in terms of momentum, it now says to us that the net force acting on an object is equal to the rate of change, of momentum. And I took that away, that's why. Okay. Oh, why doesn't it want to write for me? All right, we'll get back to that. And it's in the direction of the net force. So, normal Newton's second law still relates to the direction, okay? So you've got to have direction in there. But now, instead of doing all those other things, it's equal to the rate of change. Guys, that word rate cannot be left out here, because it's not equal to just the change of momentum. It's equal to how quickly the momentum changes. That's really important to get here, okay? It's not just about the change. It's about how quickly or slowly it happens. So here's our next equation, where F net equals delta P over delta T. That's our equation. Change in momentum, now I didn't write it like that just now. Remember, change in momentum means that it's PF minus PI. Now, if we go through all the maths again, that means that this is going to be M VF minus M VI. I take the M out. I just want you to see that we can write this another way. So we get M delta V. So sometimes you're going to see the equation written as F net equals M delta V over delta T. Now, of course, with it being written that way around, what are we assuming? We are assuming mass remains constant. Okay? That's the assumption we're making. If we look at this, we're saying mass is a constant. So, F net is the net force. The direction of the change in momentum, because it's still a vector, is the same as the net force. Change in momentum, still in kilogram meters per second, and of course time is the time interval in seconds. Okay? Now, we've only considered what happens when the velocity changes. But Newton's second law in terms of momentum is actually very useful for something else. And that is for when a rocket gets launched, okay? So a spaceship, a space rocket, whatever, we launch something up in the air, and we try and work out what the acceleration is. So we go, okay, we have a net force acting on the object, and we go F net equals ma. The problem is the mass is changing. There's, at the bottom, by the engines, okay, there's a lot and lots of liquid hydrogen, lots of liquid oxygen, because they use a hydrogen fuel cell, essentially. There's lots of this gas and liquid that then gets burnt up. That creates the upward force that pushes it, okay? And that upward force actually remains constant. What happens is now the mass is decreasing. So the mass is getting smaller and smaller and smaller in order to help it accelerate. But how can we sort of work that out? Because I can't work out the acceleration here because the mass keeps getting smaller. So the acceleration is actually changing. But if I look at it in terms of this equation, they can actually predict how fast my rocket will be going at a certain time, because this will become final mass with final velocity minus initial mass with initial velocity over time. And the whole point here is that this net force will remain constant. And as the mass gets smaller, the velocity can get bigger. So it helps it accelerate. So when an object like this has a changing mass, Newton's second law in terms of momentum becomes very useful. The first law doesn't help us here because it needs a constant mass. Okay? The first statement of it. What I need you to get here, okay? Okay, I've done that, is this. Before we say goodbye for the end of this lesson. There are two statements now that you know for Newton's second law. You must still know both, okay? This is what you've got to be paying attention to when you read your exam. If they just say, state Newton's second law in words, you can use either statement, okay? So you can either go, when a net force acts on an object, the object will accelerate in the direction of the net force with an acceleration that is directly proportional to the net force and inversely proportional to the mass. Or you can tell me that the net force acting on an object is equal to the rate of change of momentum in the direction of the net force. Doesn't matter, because they've said Newton's law, second law general. However, if they want the momentum statement, they are going to say to you, state Newton's law in terms of momentum. If you don't give the one with the rate of change of momentum, they're going to give you naught, because you haven't answered the question. They may, though I haven't seen it very often, say, state Newton's law in terms of acceleration. Then it's the long one. Okay, so please don't go, I'll learn one and not the other. You must know both, because they'll be asked in different contexts. Okay, so if they're going to ask Newton's second law while busy with a momentum question, they'll want it in terms of momentum. But of course, it's a section on its own with Newton's laws. Okay, lots to think about. Think about how we got to the equation. And in the next section, next part of the lesson, we're going to look at some application. So I'll see you in a couple of minutes. Welcome back. So you've had a little bit of time to think through what we were talking about, which was changing momentum, and we were looking at Newton's second law in terms of momentum, and it was a little strange, but it's okay. Now we're going to apply. Where do we use this? Okay, so let's look at the question. So we have a hockey player who strikes a stationary hockey ball. Stationary means, and I'm hoping you're all screaming at the TV for me, initial velocity is 0. Okay? The hockey stick has a mass of 550 grams. That's an average hockey stick. Before striking the ball, I'm referring to the hockey stick, is traveling to the right at 45 meters per second. The hockey stick is in contact with the ball for 0.0005 seconds. The velocity of the hockey stick after striking the ball is 40 meters. So I've given you information to do with the hockey stick. There's lots of things to think about here. So how do we work this out so we can make sense of the information, okay? So this is what I like to do, okay, is I like to draw a picture. Now, I can't draw. I'm not an artist, okay, much to my horror. So it's a representation. It's not going to be artistic, but it's for me to understand what's going on. So what do we have? We have a hockey stick. There's my hockey stick. 550 grams. we have our hockey ball, which is, they don't tell me because it's not actually important at this point. My hockey stick is moving at 45 meters per second. Then it hits the ball. That's the collision. As a result, my hockey stick is still going to the right, but now it's going at 40 meters per second, and my hockey ball, theoretically speaking, should be going to the right as well, okay? If it's not going to the right, then something's gone very wrong from a science point of view, and we will ignore that, okay? They also tell me that my collision here acts for 0.05 seconds. It's very, very, very quick. Now they tell me, calculate the average net force acting on the hockey stick during its contact with the ball. Net force. As soon as we see the word net force, we must be thinking Newton's second law. Okay? So, I could go F net equals ma if I could work out the acceleration. I can't actually. The issue here is that the acceleration isn't constant. Okay? It all depends on the contact with the stick. So, and the acceleration is in two directions, essentially, especially when we look at the ball. So, not going to happen. But I know final velocity, I know initial velocity, I know mass, and I know time. All right? I didn't give myself enough space. So I'm going to take away my diagram, okay, because hopefully you've got that. And now, oh, I need a bigger eraser. It's got to be slow. There we go. So, yep, F net equals, well, it's change in momentum over change in time. But remember, we also said that it can be mass times change in velocity over time, which means it's mass, final velocity, minus initial velocity over time. Okay? You can use any one of those equations. So when you write this down, you can write down any one. The first one is the one that's on your information sheet. Okay? Now I'm going to substitute in what I know. So I know that the ball is 550 grams, but can we work in grams? You should all be going, no. We have to work in kilograms. So we have to remember that there's 1,000 grams in a kilogram. So I'm going to divide by 1,000. So it's 0.55. I'm not going to worry about the zero. It's not important. Then final velocity was 40. Initial velocity is 45. And here's our time. Now, I have a small number minus a big number in the bracket. That's going to mean that I'm going to get a negative net force. But is that right? We'll talk about it now. So, calculator, okay? So we're going to go 0.55 times, now I need to use my brackets, 40 minus 45. I like to do it like this. So now we're going to get equals. That's the top part of the fraction. Now I'm going to divide that answer by 0.0005, okay? And I get an answer. It's not a fraction, which is great. Remember, we don't work with fractions, okay? Your final answer must be a normal number. Oopsie, wrong way. There we go. So, minus 5,500. What does that tell me? That tells me that the net force is in the opposite direction to which the object was moving in. Now we've got to think about this and go, negative force means that the acceleration will be in the opposite direction. Acceleration in the opposite direction means that it's going to slow down. That makes sense. It did slow down. So this is 5,500 newtons. Now, it was originally going to the right, so now it's going to the left. This is now the question. Where did that backwards force come from? Okay, let me just put this down. The hockey stick is hitting the hockey ball. Remember now Newton's third law. The hockey ball is going to push back on the hockey stick push on ball, ball push on the hockey stick. So it's the force that the ball is exerting on the hockey stick that makes the hockey stick slow down. And it's the force that the hockey stick exerts on the ball that's going to make the ball move. Are those forces the same? I'm hoping I'm hearing lots of yeses. Absolutely. Remember, Newton's third law says to us that when body A, hockey stick, exerts a force on body B, hockey ball, the hockey ball, body B, exerts an equal force, same size force, in the opposite direction on object A, the hockey stick. So when they're in contact, they're exerting the same force on each other. This is important, okay? Now, ooh, look, why was it important? The mass of the ball is 165 grams. That's the average mass of a hockey ball. Initially, the hockey ball was stationary. They want you to calculate the ball's horizontal velocity when it leaves the hockey stick. Now we've got to be careful. We know that initial velocity is 0. Okay. My mass is in kilograms, 0.165. They want final velocity. We've just said that it's going to experience the same net force. So, F net, now we've got to think about this. For the hockey stick, F net was negative because it was to the left, okay? Because the hockey stick was pushing the ball to the right. Same F net, so it's going to be 5,500 newtons. But it's going to be a positive F net because it's going to go to the right. So this is 5,500. Now we look at this and we go, hang on, I can do this. We know an equation that has F net, mass, and change in velocity. So if we go back here and we go, well, F net equals mass, change in velocity over change in time. So I'm just going to push you a little bit with your maths here. This is 550. 5,500! I will get it right eventually, okay? Just go with it. Mass, 0.165. Final velocity is what I'm looking for. Initial velocity is 0. Now, time. There was no time on this. This is important because I see this all the time. The hockey stick and the hockey ball are in contact for the same amount of time. So we knew that was 0,0005. I can't say that the hockey stick experienced the net force for longer than the hockey ball did. Because once the hockey ball's left, there's no force on the hockey stick. Okay? So my time is the same. Now we have a maths issue. Okay? How you solve this is up to you. I fully understand that there are some of you who can put this straight in your calculator, you're all happy. Some of you, Not so much. It's okay. Let's do all the maths. So first thing I'm going to do is I'm going to take the 0,005 over. And I only like to do the calculation at the end. So I'm going to have to times both sides. I would do my multiplication. I multiply that 0,165 in. But I'm going to leave out the second term, okay? Because 0,165 times 0 is 0. I want VF on its own. So VF is going to be 5,500 times 0,005 divided by 0,165. I've got it into a format that now I can put on my calculator. And we absolutely need to put this on our calculators, okay? I can't do this in my head. So let's just put the calculator over here so we can see all my numbers. So we've got 5,500 times by 0.0005. I push equals. Now I'm going to divide that by 0.165. Fraction answer, what have I said to you? You can't leave it as a fraction, so we're going to turn it into a decimal, and we get 16,67. All right, remember, we always round off to 2 decimal places at least. Okay, your instructions always say to at least 2 decimal places. If you want to use more than that, go for it, but I do not suggest you keep lots of decimals. It's just going to make it difficult for you. But we're not done. They want the horizontal velocity. I've got the velocity, but what is missing? Velocity is a vector, which means we need to give it a direction. It worked out to be a positive value, so that means this is going to the right, because it's a positive value. Okay, lots to do here. But the thing with Newton's second law in terms of momentum is we're still using Newton's third law, because when they're in contact, they exert the same force on each other. Okay? Now, how would using a softer ball affect the contact time between the stick and the ball as well as the ball's final velocity? Very important now. We apply the same net force. Now, when the hockey stick hits the ball deforms a little bit, okay? If it's a hard ball, it deforms small amount, and it's a quick contact. It makes it in contact for a quick time, okay? But if we use a softer ball, the contact time is longer, okay? So it deforms more. It actually squishes more, and you can't see it. If you go and look at videos online and you get ones where they slow down the ball, you can actually see balls almost go flat and then they come out. So if we use a softer ball, it's going to take longer to get flat. If it takes longer to get flat, the change in velocity actually has to be more. Ooh, now we're like, how does that work? Well, remember, F net is m, change in velocity, over change in time. I've said to you, that is a constant, okay? So whatever I do to the values here, I need to get the same answer, F net. If I make this number bigger, so I make the number at the bottom bigger, one of these has to get bigger as well, but the mass is constant. I said a softer ball, not a lighter ball, okay? So mass is constant. In order to get the same calculation answer here, my change in velocity must be bigger. My initial velocity was 0, so that means with a softer ball, hitting it with the same force, I'm going to get a bigger velocity, because the change in velocity has to increase because the change in time got bigger. So if we use the harder ball, I'm not sure you can get one harder than a hockey ball, I have to be honest. I have been hit with one of those. It's not nice because they're hard and anyway. If I got a harder ball that then I could make the contact time less, I would have less force. Okay, so actually in hockey it's a good thing you work with a hard ball, because then the ball would go even faster. Okay, but the key to this is that the F net stays the same. Okay, if instead I said to you that the ball goes off with the same velocity, I could then ask you what would the F net be? Well, this time, if I'm keeping, let's just write this again because now it's getting all messy. So this time, I'm keeping that the same, okay? But I'm making the time bigger, so I have the same number divided by a bigger number, which means the answer will get smaller. So with a softer ball, to get the same final velocity, I would have to exert a smaller force. Wouldn't need the same force because it's easier because of the contact time, okay? And we're actually going to spend time on that when we get to impulse, because that difference in time and F net becomes very important when we look at car safety and why we wear seatbelts and why we need airbags and all of those sort of things, okay? So let's do the summary. So Newton's first law, okay, which we know, and I haven't written out because it's one of those things. Then we've got Newton's second law in terms of momentum. Please, you must learn it. The net force acting on an object is equal to the rate of change of momentum of the object in the direction of the net force. Please don't forget out, because I see this as well, and this is one of those things, direction of the net force. Please don't forget that. Then we had the equation, F net equals delta P over delta T, okay? Remember, we can make that final momentum minus initial momentum over delta T, and we can also write it as mass times final velocity minus initial velocity, which is m delta V over delta T. Okay. This is the equation that's given to you on your information sheet. So, that gets us to the end of this lesson. Hopefully you've got it all in and you're going to go and think about it. Lots to think about, but it's okay, we did well, and I will see you next time.
Siyabangena! Woza Matrix is back and better than ever, with catch-up lessons, revision and learning support on more platforms than ever before. There are great support materials on the DBE Cloud. Find us on television and revise 10 subjects. And if you miss something, relax, Ntwana. Go to our YouTube channel or DSTV catch-up. Need help? Check out Vele, our Telegram-based chat platform where teachers are waiting to help you. Prefer WhatsApp? Send questions or voice notes to our Woza Matrix WhatsApp line. And that's not all. Want to test yourself? Check out the Matric Live app. Hey Matrix 2021, we've got you covered. Confused where to go? Visit the Woza Matrix website at wozamatrix.co.za. Woza Matrix.